So we're continuing on talking about electromagnetism. So today we're going to be focused on uh, the magnetic field produced by a current carrying loop of wire, and then we're going to build on it, talk about loops of wire together, or a coil of wire, aka a solenoid. So starting off talking about a loop of wire, building off of what we learned about the magnetic field around a long straight wire, I can use the right hand rule to still kind of figure this part out. Okay. So I got a magnetic field here. I've got a wire, I should say. I've got the loop of wire here. It's connected to a battery, positive in there, negative in there. The current goes this way. I know that there's going to be a magnetic field uh, in the inside of the loop, and there's going to be a magnetic field coming around the outside of the loop. And the big question we're going to start off with is asking, what direction is this magnetic field going? And is it different on one side of the loop than on the other? All right, so starting off, right hand rule. So if I put my thumb in the direction the current's going, so it's down here, it's going that way. Over here, it's going that way. So if I put my right thumb in the direction the current's going, it looks like the current is coming out of the screen around the outside. I probably should have done these circles bigger. I was in a little bit of a hurry. Okay, it looks like the magnetic field's coming out of the screen at this point. It's represented by just a circle with a dot in it. And it means around the entire loop, the magnetic field's going into the screen all along the inside. And this is pretty uniform, which works out really, really well. So the magnetic field, in this case, if I reverse the current, if I simply turn my battery around, have the current go the other way, it's simply going to reverse my X's and my dots, okay? The electric field is going to be coming out of, let's see if I can figure this out. It's going to be coming out of the middle of the loop and into the outside of the loop. It's just going to reverse the magnetic fields as well, which is really important for something coming up. So that's through one loop, and the magnetic field that one loop would produce would actually be pretty noticeable. You could measure it. You could actually use that magnetic force to do some stuff. What we're going to do is not work with one loop. We're essentially going to take a lot of loops and connect them all together. So let's say I've got a loop here, and let's just say that I have where I'm at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say that we're going to have 10 loops. Okay, so let's go positive, negative. So we send a current through it this way. Really what we're going to see is now I've got a bunch of loops all together, and since the current's going in the same direction through each loop, that magnetic field inside the whole loop is all going to add together. And really what we should see is that the magnetic field is going to go this way through the loop. And then just like what we saw with a magnet, it's going to loop around and kind of come out here, okay? And granted, I'm only drawing one magnetic field line. There's a bunch of them. In fact, let's even draw a couple of them to show that it's kind of coming out this way, coming in this way. And let's even draw just one more. Go through my curve. There we go. A little messy there, but that's fine. All right. Really what we're really going to find is that the magnetic field is really, really strong on the inside of the solenoid. And it's a little bit weaker towards the middle. So now I can finally address, so what is this equation going to tell me? Really, this equation is going to tell me the magnetic field strength, which is still B, still measured in Tesla. Really, it's just going to be equal to the permeability of free space, still fun to say, times the number of coils in my solenoid divided by the length of the solenoid times the current going through the wire. Okay. So really, let's go down and, uh, you know what? I'll even leave my examples there. Okay. I'll just rewrite it. B B is equal to the permeability of free space times number of coils divided by length of the solenoid times the current. All right. Now I can look at this practice problem down there. So we've got a solenoid, and I'm just going to do it kind of like this. We're going to use our imaginations a little bit. We're going to say that my solenoid here is 20 centimeters long, but it contains 200 loops or 200 coils. And let's even convert this. I know for the most part my equations aren't going to be able to use centimeters, mainly because my permeability of free space is in meters. 20 centimeters is 0.2 meters, okay? And the current going through this wire is 3.25 amps, okay? They want to know the strength of the magnetic field inside the solenoid, so they want to know B. So really all I'm going to do is I'm just going to plug in what I know. So B is equal to the permeability of free space, which is still 4 pi times 10 to the negative 7th. I'm actually going to pop it in parentheses for now. Tesla's meters per amps. This would be equal to or times the number of coils, so 200 loops, over the length of the solenoid, which is 0.2 meters, times the current, so 3.25 amps. This math, I actually will need a calculator for this one. It's not quite as easy as the last one we did. Math just isn't quite that easy all the time. All right, so I've got parentheses. Let's go 4 pi times 4. Okay. Times 10 raised to the negative 7th, close parentheses, times open parentheses, 200 divided by 0.2, close parentheses, times 3.25 equals. So that magnetic field is equal to 0.00408041, I think is what I'm going to go with. 0.00, actually, let's go, 41. And keep in mind that's Teslas, okay? Because meters is still going to cancel meters, amps cancels amps. So we're still at meters, okay? So that's the number of Teslas that is produced by a 200 loop solenoid with a 3.25 amp current going through it. That's a pretty decent electromagnet, I think. That'd be enough to pick up paper clips for sure. It'd be pretty easy enough to make at home. One of the things that we are going to learn in physics is that if you really want to make a solenoid a lot stronger, you could put an iron core in the middle, and that increases the strength of the magnetic field big time. It makes it way stronger. But I just kind of want to go through the equation for the magnetic field produced by a solenoid without an iron core, just help out with the practice problems. With that, good luck.